Bonding is a mechanical means used to establish electrical continuity between conductive components so that all of those conductive components maintain an identical electrical value. That electrical value is determined by what is being bonded. Here, a de-energized conductor is bonded to an effective ground using a grounding cable. Therefore, the shared electrical value is now at a 0-volt system reference. On the other hand, here you have a 5,000 volt energized conductor bonded to an isolated conductor laid out on a hot arm using a hot MAC. Therefore, the shared electrical value is now 5,000 volts. An effective ground is an electrical point of connection that establishes a 0-volt reference with regards to the system. Examples include ground grid leads in a substation environment or even the structural steel that is bonded to them. These are effective grounds because they are bonded back to the system return or the system ground reference. However, the static wire on the pole in this particular case is not an effective ground since it is not bonded back to the system return or the system ground reference. This also means that the pole ground on this particular pole is not an effective ground, because even though it is bonded to the static wire, we've already established that this static wire is not bonded back to the system return or the system ground reference. Therefore, by association, neither is the pole ground. In both of these instances, the voltage potential is routed into the earth, which is an example of earthing which we'll elaborate on here in a minute or two. So should an electrical fault occur between the energized phase and this particular pole ground, then that massive amount of fault energy will be routed into the soil where it must then push its way through literal tons of soil resistance before reaching an effective ground. The same applies to the temporary ground rod as shown here, as well as any vehicle or equipment bonded to it. That massive amount of fault energy is routed into the earth where it must then push through tons of soil resistance before it ever reaches an effective ground. The bugger with not being bonded back to an effective ground is that the circuit may or may not activate. The reason being is that by the time the fault energy reaches an effective ground, the energy level may be too low because it was knocked down so far while pushing through those tons of resistive soil. If this is the case, then the circuit protection may not identify it as a fault. It may interpret the large amount of current as an increase in load demand, thinking the entire neighborhood just turned on all of their air conditioners at the same time. If that's the case, then the system is just going to keep pouring the juice into the lines. And if the circuit protection doesn't de-energize the circuit, then that massive amount of fault energy will continue wreaking havoc on the system, anyone on it, and everything connected to it until something burns to the ground. And, well, maybe not even then. Grounding is the bonding of a conductive object to an effective ground with the purpose of extending and maintaining that system's 0-volt energy reference. Here, the substation ground grid is an effective ground because it's bonded directly back to the system return or the system ground reference. And since the steel structures are bonded to this effective ground, which in this case is the ground grid, then those steel structures are also considered grounded. Let's say you bond the isolated and de-energized Y phase to the grounded steel structure. If so, then Y phase is now grounded as well. And daisy chaining phases X and Z to Y phase now ensures that these phases are also grounded. The man lift is grounded since it is bonded directly to the substation's ground grid. Bonding the man lift to the structural steel will also have the same effect since the structural steel is bonded to the system's ground grid, which has already been established as an effective ground. It's all pretty much a game of connect the dots here, but as simple as it may seem, don't get complacent. You must understand that grounding itself is not equipotential or personal protection. Conditions such as voltage rise and induction must always be taken into consideration on a case-by-case basis because they may still be present and continue exposing a worker to the hazards of touch potential. The difference between earthing and grounding is the presence or absence of an effective ground. If you can trace or connect the dots of all your connections back to an effective ground, well, then you have grounding. If you can't, well, then you have earthing. Grounding is essentially eliminating the resistance between a component and the effective ground due to its direct or indirect mechanical bond, which in the examples we've been covering are the circuit grounding cables and the vehicle grounds. Earthing is the attempt to minimize the resistance between a component and an effective ground due to the lack of the mechanical bond. This dead short, no resistance mechanical bond has been replaced with the variable resistance of the soil. Cases can include when relying on the pole ground, a temporary ground rod, and in some cases, maybe the overhead static wire when it is being used solely for lightning protection, which we'll discuss here in a minute. Keep in mind, The key of earthing is the absence of the effective ground, because without this effective ground, there is no 0-volt energy reference with regards to the system. The digger derrick on the right is grounded because it is bonded directly to the system's ground grid, which provides a direct mechanical path back to the circuit's protected device, which would be the fuse, circuit reclosure, circuit breaker, what have you. The digger derrick on the left is earthed because it is bonded to a temporary ground rod that has no mechanical bond that can be traced back to the system ground reference or system return, and therefore not back to the circuit's protective device. Tons of resistive soil now lie between the temporary ground rod and the effective ground, and any energies channeled to the soil under these conditions must now fight through tons of resistive soil before reaching any semblance of an effective ground. Lightning protection is a form of earthing. Lightning protection's primary objective is to intercept a lightning strike and channel those massive energy levels into the Earth's soil, where they may then be effectively dissipated by the soil's cumulative resistance. Lightning protection is not always bonded to the system ground reference or system return, and until determined otherwise, it should not be relied on as an effective ground.